last time. So we're working on Zaremba. We have A is some alphabet, finite alphabet, although finite is not essential. RA is the set of all fractions, B over D.
Like in the thesis you showed us, that it says the alphabet of all evens, right?
For example, yeah. So finite, sometimes not. Alphabet. RA is the set of all fractions. DA is the set of all denominators for which there exists a numerator co-prime to it with B over D in RA. And what we want, and N is admissible.
It's weird. It's like we're asking for a terrible approximation. And so
Yes.
That's sort of like what
Yes, uniformly badly approximable. Yes, exactly. N is admissible for the alphabet A if N is in DA mod Q,
right.
for all Q.
But in Q here, you're asking it for be all numbers. Or
All-
you're asking
All integers.
all integers.
Yeah.
It's not like you're asking for just primes.
No, not just primes and not just prime powers.
Right. So
So
usually
there's some-
it's harder than just Chinese remaindering for prime powers.
It's not harder. It's not much harder. But there's some, you have to be a little bit careful. Right, and then we defined this semigroup gamma A, which is the semigroup generated by things in the alphabet, semigroup. And this is how we understood all of the modular restrictions through strong approximation.
Yeah.
And now we're going to actually start doing something.
And the way that you did this was by proving that it sufficed to look at the group generated, right?
Yes.
Because mod P would
In
be
this
the same
case,
thing.
yes, when A is 1 and 2, for example, when A is the set 1, 2,
Wait, so there are other sets where you have to be more careful.
that's exactly what Huang's thesis was.
Oh, okay. Just dealing with okay.
Yeah, all are admissible. All are admissible. So that's how you could show something like this. And that's also, okay, so let me remind you of Hensley's conjecture. Hensley / our modified version of his conjecture is if the Hausdorff dimension of this alphabet is bigger than a half, that's one obstruction at infinity, and N is admissible. That's all the local, all the finite prime obstructions. This is the finite primes obstructions, and N is sufficiently large, depending on the alphabet. So these two are the infinite prime obstructions. That's how I'm thinking of them. Then N actually occurs in the set of denominators. So every sufficiently large admissible number occurs in the set of denominators as long as it can. That's the conjecture.
Right, admissible. Yeah, that's the original Hensley conjecture. They don't worry about admissibility.
He missed that there could be. Now, again, if the dimension is large enough, then admissibility is automatic. Huang, if dimension is sufficiently large, greater than, I forget what it was, 0.7 or something. So what is, okay, 0.7, then all N are admissible. And of course, that's not a necessary condition because this dimension is just above a half. So you can have all numbers be admissible and have a smaller dimension. But if you want to guarantee that any alphabet,
Right.
regardless of the alphabet, as long as the dimension is sufficiently large, every N is admissible, then Huang identifies exactly when that happens.
And he identified, right, the maximal
The maximal dimensions and the alphabets.
which is failed.
Yep.
Right? Yeah.
Okay, so so theorem, again, this is with again, is that if delta A is sufficiently large, 0.999 or whatever. And this has been whittled down to better things. I'll give you some hints on how to do that. I just want to give you some hint on how to do this. If the dimension is sufficiently large, then the number of elements of D up to n relative to n is 100%. Okay, as n goes to infinity.
Which was the best that had been done by a long shot.
Right, not even positive proportion was known at the time. Okay, let's do it.
Yeah.
Okay, so idea one is the circle method. So what are we going to do? We're going to make a representation number. Make a representation number. Well, we already know what a representation number is. It's like a multiplicity. Representation number. I'm sort of switching to the language of Hilbert's 11th problem on numbers represented by quadratic forms. So this is the same thing as multiplicity.
So where are we going to let that count?
So let's let R sub n of little n be a sum over gamma in this alphabet, gamma A, in a ball of size n, and then the indicator function. Now, if we have an element gamma in our semigroup, remember, why do we care about gamma? It's because when we take a word, A1110 up to AL110, we get this D in the 1,1 entry, DB, whatever.
Yeah.
Right? So the D is the 1,1 entry. In other words, you take gamma, you multiply it by E1. E1 is 10. And then you take the inner product of that with E1. And that's D.
Yeah.
Okay. And that, I want to know if that's equal to n. Okay, so I take elements in gamma in a ball of size n. Now I'm going to do this with n of size n. So I fix a big ball of parameter capital N.
Okay.
I look for n's between, let's say, n over 2 and n in some dyadic interval. And I want to know how many times is that particular value of n represented as the 1,1 entry of a matrix in this ball.
So like Bn minus Bn over 2, something like that.
This, you mean Bn or
The section Bn minus Bn over 2.
Sure, but
No, okay.
I'm lying in all kinds of ways, so it almost doesn't matter how you interpret this. Just take a big ball in the group, in the semigroup, and then how often does the number n occur? How often does number n occur as this? It's exactly what we were calling a multiplicity.
Okay, we that inner product because that gives us D, the upper left entry.
Yes,
Okay.
yes. This we could also write as d sub gamma. In other words, i.e. gamma is equal to d and then whatever. Where d is n. I'm trying to catch out. This is what we were, if n, let's say n is less than n, then this is also the multiplicity in this alphabet of the number n. Because you don't need a ball, once you're trying to make the number d occur here, as long as the ball is large enough, as long as the ball is larger than the ball of capital N is larger than the element you're looking for, little n, then this is exactly the multiplicity. You didn't have to cut it off. This is a useful technique because we're going to want to prove things for a range of n's. So we don't want to change the ball every time we don't want to change this ball every time we're looking for a different d. Okay. So far, so good. Okay, and the obvious thing is that if Rn of n is not equal to 0, then n is in dA.
Yeah. Where's the appeared once?
Because it appeared at least once. If it appeared 0 times, then okay, we don't know. Well, then it's not there. But in a minute, we're going to change this.
Right. Okay,
this
we're
function.
only choosing gamma in gamma A, or sec B on. So
Yes,
you're not gonna get some sort of illegal number out of it.
we're not going to get a legal number out of this. That's exactly what this says.
Okay.
If this doesn't vanish, then it doesn't vanish because we actually found some element of DA. That n for that value of n is an element of DA. Okay,
Wait, and what you were saying before, it's like, you're saying, is this sum finite without the ball?
this sum is finite without the ball because the D element will always be the largest one.
Ah, that's what you were saying earlier. So it's like once you're allowing bigger,
In more general settings, you need to truncate this sum so it's not an infinite sum, which with potentially infinitely many multiplicities. So for example, in SL2Z, how many elements have a 5 in their top left
Right,
entry?
right,
Infinitely many.
as long as you
Okay,
relatively
so-
prime, then it's,
Yeah, so you have to cut off the ball just for this fun sum to be finite. But actually, we want to deal with n's in a range. And so we want to have a uniform. We don't want this to also change when n changes. Since our theorem will anyway be an average theorem. So we want to separate the ball, have one fixed ball, and show that for all n's in a range with that one fixed ball, we have representation. Okay, what makes it the circle method? It's that you recognize, well, this isn't the circle method, this is the trivial thing, which is to write this as the inverse Fourier transform as the nth Fourier coefficient, e of minus n theta, d theta. So I'm just doing stupid, Fourier analysis on the circle, and where r hat of n of theta is just, okay, well, technically it's the integral of this, it's the dual, the circle is the dual to the integers. So it's the sum over all n, Rn of n, e of n theta. I don't know where I want the plus sign, here or here. Let me put it here, e of n theta.
Yeah, this is the usual way, I think.
Okay,
and then,
This is a finite sum,
well, it turns out to be a finite sum, exactly.
everything is nice.
So everything is nice. Yeah, there's no convergence issues. You're integrating over a compact region. Okay, so this is another reason not to have an infinite sum here and not to have capital N be equal to little n.
right, so if we're infinite, you'd have to say something else.
We'd have to be a little more careful. Yeah. But there's a better expression for this. Sorry, Leo.
I'm just thinking, I've seen that technique before, yeah, I'm just trying to connect the dots.
Yeah, so this is just the Fourier transform. You have a function on the naturals. Its dual is the circle. You sum these finite things, you stick it back in here. This is complete triviality. Another expression for this, if we put in the definition of Rn, is that it's a sum over gamma in gamma A in a ball. And then this indicator function, summed over all the integers, will exactly pick off when n is equal to this value. And when it's equal to this value, it'll be this exponential sum. So it's just e of theta times this value, e1 gamma e1. Let me just call this e so I don't have to write ones everywhere. The only e that will appear, oh, will that conflict with this e?
Ooh, yeah, that's
Fine.
you could give it a different letter.
I could give it yeah, let me give it a different letter. Let me call it v.
Yeah.
So there's some little vector here that we're taking our inner product with respect to.
I don't see I don't see it yet.
Okay.
It's a sum and then a sum, Rn is a sum, right? Rn
Yeah.
is a sum of all.
Rn is a sum.
Then you flip them,
I flip them.
and then you only pick what will survive. from
Yes, there's only one value of n that will survive the n sum, and that's the value when n is equal to this.
Because if n is equal to that, then you get a 1.
Then you get e of n theta, but n is equal to this inner product. Let's do it again.
Yeah, I'm sorry.
I have a sum over n, which will be a sum over gamma in gamma in a ball of size n. And then this indicator function. So a sum over n in z, Rn is this indicator function. This indicator function that n is equal to v gamma inner product v. And e of n theta.
Okay, yeah.
So far, so good. The only way this can not be zero is if n is equal to v gamma v.
N is equal to,
This is zero only when,
oh, you mean like literally?
Literally.
Definition.
yes.
Okay,
So I'm going to replace this by e of theta gamma v gamma v. I'm just replacing n by v gamma v because the only place where they agree.
Right.
And now this sum, well, one integer is exactly equal to, so this now pulls out. This doesn't depend on n anymore.
Okay,
And then this summation has only one value of n for which it picks up a 1, and for all other values it's 0.
ah,
So this is just 1.
yeah, I got it.
No worries. So here's our exponential sum. In fact, it's, if you think about it, it has to be the Fourier transform. You're taking the indicator function of this set. The Fourier transform is exactly the exponential sum where you stick in a theta, where you make out of this integer, you make a number of absolute value 1. Okay, so far this is just utter triviality. We haven't done anything. The key idea of the circle method is to capture, so key idea of the circle method, this is not the circle method, this is baby Fourier analysis. The key idea of the circle method is to capture, I'm having a brain freeze, this integral on 0, 1 as an integral over so-called major arcs and minor arcs. So these are going to be the major arcs, and these are going to be the minor arcs.
And this was done for the first time for representing sums of cubes or something?
A little bit before that is Waring
Waring
problem,
problem? That's like for what?
and even a little bit before.
Polynomials or something?
Waring's problem is that representing a number as sum of 4 squares,
Right.
or sum of 46 fifth powers, or whatever. How many powers of Waring's problem was, is there some number so that if you take 17 powers, you add enough 17 powers and you'll represent every number or every sufficiently large number or whatever.
And then was this problem like an easy application of the circle method, or is it just happen to be the first place where?
Well, it was where the circle method was developed. So it's easy now to say that it's easy after 100 years of
Oh, yeah,
technology.
I definitely meant in comparison to other applications of circle methods.
Yeah, so
Not
really,
so much,
Hardy and Ramanujan used this kind of idea to study the partition function.
Right.
That's like, yeah, maybe I should say a little bit of the history.
Like, additive number theory kind of stuff,
Right. So Hardy and Ramanujan
generating functions.
looked at the partition function. In other words, the number of ways of writing partition function. A number of ways of writing, P of n. So P of 5. That's the only one I can work out. You can do 5 is 1 plus 1 plus 1 plus 1 plus 1, or it's 2 plus 1 plus 1 plus, maybe 5 is already too big, or it's 2 plus 2 plus 1, or it's 3 plus 1 plus 1. Let's see, what can I do with just ones? I can have 5 ones, or I could have 3 ones,
Yeah.
or I could have 2 ones, or 1 1, which could be in several ways. Anyway, you see the point. This is like not so easy to work down. And 3 plus 2, and I'm done. Okay, and one more, 3 plus 2, and that's 1, 2, 3, 4, 5, 6. So the partition function takes value 6 at 5. Okay, so general asymptotics. Now this function grows exponentially.
Right.
So getting asymptotics for this was an open problem, and it was solved for the first time by this kind of an idea.
Really? That is what they use for using this kind of idea.
Yeah, and then Hardy-Littlewood took this much farther, and then Klosterman took it even farther than that.
What do you mean by farther? You mean like
Well, we'll see. I'll show you some of the
Okay, okay.
techniques
I mean technique-wise.
technique-wise, yes, and application-wise. So Hardy-Littlewood did this with Waring's problems, exactly as we said, Waring's problem. And they could also do quadratic forms and they needed quadratic forms in 5 or more variables for their circle method to work. And Klosterman got this to work in 4 or more variables. So quaternary, he was able to do what some people call Klosterman's refinement. Other people like to call this just Klosterman's method, because it's a really a slightly different idea, which is not to break up into major and minor arcs, but to have everything be major arcs. So you have an exact decomposition of the circle as opposed to some loose decomposition. But even loose decompositions, you can still use some of Klosterman's ideas to get extra cancellation. We're going to talk a little bit about this
Interesting.
for quaternary.
They call it method because it's not quite the circle method since there aren't minor arcs.
Right. So numbers represented by quaternary quadratic forms cannot be handled by the sort of Hardy-Littlewood circle method, but can be by Klosterman's refinement or by Klosterman's method. Okay, let me show you what major arcs and minor arcs are supposed to be. So I had a picture that I drew here. Hello, may I please click on you? No, I may not. That means I have to scroll. Sorry? Okay, so just to give some flavor, here's what this R of theta looks like. Of course, it's a complex. So this R hat of theta, R n hat of theta, as a function of theta. Theta goes from 0 to 1. Okay, it's a complex valued function. So let's look at the real part or something.
But yeah. Okay, now I'm saying so. It's like if you have like a fractal kind of thing, it makes sense to treat something like gaps differently than other stuff.
Well, depending on the value of theta. So like if theta is equal to 0, okay, let's see about theta equals 0. What happens to R n hat of 0? Let's look back at what R n hat is. R n hat is this exponential sum. When theta is equal to 0, it's just the number of elements in the ball. It's exactly the number of elements in the ball, which we, if you recall, is n to the 2 delta. I mean, let's just be crude. I'm not going to put epsilons. Okay, so that's here. We're going all the way up to n to the 2 delta. This huge spike. Exactly. And by the way, every value of theta, just by the triangle inequality, is no bigger than the value at 0, because these are all things that, okay, so that's the biggest it'll ever get, and it'll return there at 1. Okay, so that big spike is even off the charts, and it returns to that big spike there. Now what's going on at a half? Exactly at a half, you're getting a plus sign every time the number is even and a minus sign every time it's odd. If theta is equal to a half, then depending on whether this number is even or odd, it points
plus 1
or minus 1. So this is catching the distribution. Are more of them even versus odd? What's the distribution of even values or odd values? And it turns out, well, for whatever reason, there are more odd numbers occurring for this particular value of the ball than even values. But whatever it is, it's something, there's a spike there. There's a spike with information. And so what I tried to highlight here in red are exactly the places that are close to, very close to rational numbers with small denominators. That's where there are spikes. And that's what's supposed to be the major arcs.
Oh, I see.
And in between these major arcs is supposed to be random angles. And those random angles are supposed to have lots of cancellation. Okay, so what they observed is, this is what any signal processing does. Where is the signal? There are some frequencies on the radio, you guys don't even have, I don't know if you had cars with you know, now you just push your button and it tells you 97.3 or whatever. So when you're close to a station with the signal, you hear a signal, you hear some information, otherwise you hear noise. So what's going on is
your interference of 2 channels overlapping.
that too, right? So for numbers, so the major arcs, what they observed is that the major arcs will be thetas that can be written as A over Q plus beta with Q small and beta small. So small approximations to rational numbers with small denominators.
Wait, but then what is beta? Where does it live?
Well, we're going to talk about that. It's a parameter. So beta is the kind of the distance around fractions with small denominators that we're going to try to capture.
And then the A over Q is just simply the,
It's just a fraction.
Beta is the fatness of the red line that.
Yes. Exactly. The fatness of this red line.
So then I guess the difficulty in this is that you have to do it precisely, right?
You have to-
can't be sloppy.
Yes. Yes. Okay. So there's signals. So this is supposed to be the signal. The major arcs are the signal. And the minor arcs are where on the radio you just get noise. So this should be cancellation.
So I guess in this context, it doesn't seem crazy that somebody would have come up with a method of looking at something like that.
Yeah, it was 100 years ago before there were radios and so on. But
But in general, you look at a graph, say you try to.
you look at a graph if you were to plot it with Mathematica. No, you have to.
Computations.
Yes.
Estimations.
Yes. No, it's not an unreasonable thing at all to do. It's exactly what harmonic analysis was designed for. Harmonic analysis says, where's the signal? So in number theoretic applications, the signal seems to be, I mean, there's no theorem that that's where it has to be, but the signal is fractions that closely,
Yeah.
that have small denominator and nearby such
I
fractions.
guess what I meant by my previous comment is that if you expect not everything to be uniform, right? Like you expect some spikes and maybe like not some spikes, even if you don't graph it, if you expect some behaviors to be different.
Yes.
then something like this doesn't seem crazy, right?
That's right.
Treat separate cases differently.
That's right.
Like that's not like a crazy idea.
That's right.
Do we truncate the denominators? We look at all of them simultaneously. So like 1/3, 1/2, 2/3, and all the P over Q co-prime.
You'll see in a minute what we're going to do. You'll see in a minute what we're going to do. There's going to be a parameter that determines whether the denominator is small or not. Small enough to be considered signal versus noise. There's going to be some threshold where we declare these fractions belong in the major arcs, these fractions we're going to consider minor arcs, and we're going to try to get cancellation. So let me point out, because some people get confused. Major arcs are a tiny proportion of the circle. It's not major because that's the bulk of the circle. It's major because that's where the signal is.
Yeah, right. The main term should come.
The main
from-
term, right? So the main term should come from the major arcs,
If it doesn't, then you didn't get a theorem, right? It's
Yeah.
like
but these major arcs comprise a tiny proportion of the circle. Okay, so most of the circle, which is the minor arcs, should be noise.
So does the method generally not work if your minor arcs are kind of big?
So if the minor arcs are too big, you'll have trouble extracting the signal. The happy medium is when the major arcs are just large enough. Sorry, did you say minor arcs or major arcs? I said minor arcs just now. I was
Yeah,
thinking
yeah.
major arcs. If the major arcs are too big, if beta is too large or if Q is too large, you'll have trouble extracting the signal. And so the smaller you make the major arcs, the easier it is to extract the signal. But then you have to fight against, then everything else is minor arcs and you have to be able to get cancellation. So there's this battle between major arcs.
How tight should you make it before the
Yes.
approximation?
You want to make the major arcs as wide as possible while still being able to control, while still being able to extract the signal. And you similarly want to allow the major arcs, the minor arcs, where the noise is supposed to be as large as possible while still being able to show that it's noise. So it's that battle that will determine all these parameters at the end of the day. Okay, so in order to talk about these parameters, we need, I'm sure all of you know this, we need Dirichlet's approximation theorem, just to get started. So Dirichlet approximation theorem.
It's the pigeonhole.
The pigeonhole, exactly. This is where Pigeonhole was born. as we'll see in a second. So for any parameter n, let's call it m, for any m, and for all theta in the circle, I mean, it doesn't matter that it's in the circle, it's theta in R, there exists a denominator at most m, and there exists a numerator coprime to that denominator, so that theta minus a over q is less than 1 over q times n. Okay, and the proof is completely trivial. So m is like the parameter that's controlling the quality of the total partition. There's going to be separate parameters that'll control whether we're in the major arcs or minor arcs. The proof is completely trivial. You look at the values of q. So you look at theta mod 1 and 2 theta mod 1 and up to m theta mod 1. Okay, and these are, I guess, do I want to look at 0? I don't know. So if I'm looking mod 1, here's 0, 1. Exactly, exactly. So if I look at bins that are of size 1 over m, so this is m minus 1 over m, there are m, okay, I guess I have to look at 0 times theta. Yeah, that's okay. 0 over 1 is a perfectly fine fraction. So here, there are m plus 1 values, but here there are only m bins. And so wherever theta is, and then 2 theta is over here somewhere, mod 1, and then 3 theta is over here somewhere, and so on, there has to be some bin with 2 values of theta. So there exists a bin with 2 values.
Bin is with 1 over m, right?
Exactly, exactly. So what that means is there exists a k and L less than m, so that k theta minus L theta, well, that's there's some integer values. So minus some integer, I don't know, m, these are integers. There exists an integer m, so that this difference is less than 1 over m. So that they're within 1 over m. These two values are within 1 over m of each other, modulo an integer. Okay, and now k minus L, we can write this as theta q, or let's not make it theta yet. Anyway, when you divide out, let's not make it q yet. When we divide out by q, we'll make this at least lowest terms. It's clear what you do now, right?
Yeah, you divide by q.
You divide by q,
Reduce q and m.
and you reduce q and m. Okay, 1 over q. So it's just pigeonhole. Okay. So, let's go back to this identity, and let's look at what it means to decompose into major and minor arcs. There's going to be a okay. So in our yeah, let's do it like this. So back to Rn of n, which we want to know is non-zero, which was an integral in 0 to 1. I'm just writing this again for all of us, which we split as an integral over the major arcs, which I haven't told you what they are, and the minor arcs, which I also haven't told you what they are. I mean, the minor arcs are the circle minus the major arcs. Okay, so that's easy. We'll call this sum the main term, and this sum we'll call the error term. Okay. What do we expect for the main term? How much of a discussion should we have about this? Yeah, let's before we compute, let's be a little bit philosophical for another minute.
Oh yeah, and I just wanted to ask, until when were we doing trivialities?
So
Still?
we still have not done anything of value.
It was still like baby Fourier.
Yeah, baby Fourier analysis.
For any problem, in principle, you could get to this stage.
Yes,
And then it's what you do here that's gonna
Yes.
make or break it.
exactly. Okay,
So is it the case that you were saying earlier, we want to make the major arcs, keep them small enough, but we also need to be able to control the area term, there's this balancing act. Is it the case that for something like twin primes, there's just no overlap
exactly,
of a good region?
exactly.
Handle
And when we evaluate the major arcs on the twin primes, if we make them small enough that we can evaluate them and get a signal, we get this Hardy-Littlewood constant, which tells us exactly how many twin primes there should be up to X. And that agrees beautifully with all numerical calculations. In fact, in this case, I guess I can tell you exactly what MN is. How shall I do this? Okay. Later, possibly never. Here's what MN actually looks like. It's exactly equal to, I had an REU student work all of this out.
Really? What year?
Was it 13?
Whoops, here it is. It was Peter Cohen.
2015. Oh.
And if you work out what the multiplicity should be exactly, you get a very clean formula. Okay, so the multiplicity, as long as n is less than n, in other words, the exact count, the exact multiplicity should be conjecturally, so this is a conjecture, a very precise conjecture, which one can make, is that this is asymptotic to what? The number of elements in gamma in a ball of size exactly n. You see, when you have a ball of size n, an L infinity ball of size n, the number of elements is roughly n to the 2 delta. And you want to know how many elements are right on the boundary.
Are you saying because of the indicator
Yes,
function?
yes. If you have gamma A in L infinity ball, in an L infinity ball, the largest element is going to be this D. This is the largest element. So if you look at a ball, an L infinity ball Bn, so this is a ball of exactly, this is in gamma A, a ball of exactly radius n, and then you want to know what the multiplicity of n is. The multiplicity of n is exactly the boundary. It's exactly this is the boundary of gamma A.
Aren't we taking L infinity balls?
At the moment, I'm being completely agnostic about the balls. We'll have to take very precise balls and we'll have to smooth them and we'll have to do all kinds of things to them. So the first thing is, how many elements are there? And then what's the derivative of that? Well, the derivative of that, if
the Bn gamma.
right, this is exactly how many elements there are. Now, if you know that the size of this is n to the 2 delta, right? The number of elements of gamma A in a ball is some constant times n to the 2 delta. So what's the derivative of that? Well, a 2 delta comes down and the power of n decreases by 1. And then the constant remains the same constant, which we can capture by this size.
Oh, because you're like, yeah, surface versus volume.
Yes.
That's basically what you're doing.
So that's this first thing, the size of the ball
Whoa.
times 2 delta divided by n. And then there's all the local factors. And it turns out that the local factors are just zeta of 2, and then a product only over the primes dividing n, there's some fluctuations, of p minus, I guess I would write this as 1 minus 1 over p, p minus 1 over p.
Interesting. But you guys weren't able to.
No, that's just, well, okay, sorry. The conjecture is that that's what the representation number is. That's the exact multiplicity.
Well, the exact one, you guys were able to prove the asymptotic.
So this is a computation which predicts the exact multiplicity. And the reason that's what it predicts is because you can prove that this thing will be under certain conditions. The major arcs give you this. And then you can run numerics. And here's the numerics of the ratio of the actual multiplicity divided by this expected multiplicity. And well, he didn't go that far out. In fact, someone else went much farther out for me, and this thing is converging to
Close
one.
it does.
That's good.
It numerically does seem to.
Yeah. But this is.
Yeah, from this picture, it's kind of hard. It looks like you could have some asymptotes or something.
Right.
But, you know,
So, so what one can prove, what one proves, and we'll see if I can find time to do this, is that the major arcs in our setting will be at least something of the right order of magnitude. In other words, n to the 2 delta divided by n. So let's divide by n. So this is the total number of things in the ball, and you want to get 1 over n of them. You want to hit exactly little n out of the big N values times.
For major arcs, you want big. For minor arcs, you want small.
Yes.
Okay, so, okay.
Yes, times, this is something called the singular series. Traditionally, this is called the singular series. This is called the singular integral. Singular series, which is computing local densities. So maybe we'll talk about this at some. Yeah, but the point is that this thing is bounded from below by, I mean, it's less than 1. And you might worry that it can get very small, but actually it gets no smaller than n to the minus epsilon. And it really depends on n, as opposed to this part, which is an Archimedean thing, which is uniform over all n's in a range, up to constants. Okay, so you should think of this as being, if you ignore the role of this singular series, which I'm proposing you can, is just n to the 2 delta minus 1. I mean, I actually.
Is it worse, -1 minus epsilon or something?
Yeah, there's a minus epsilon here, and it's even less than that. It's like powers of log, if you really.
Interesting.
Okay, so let's take that as a given. Let's take as a given that we can get lower bounds for certain values of the various parameters that I haven't described to you, that we can get these lower bounds on the major arcs.
Okay.
Okay, what does one need? So I claim, so if you could show that the error term, this E of n, is little o of n to the 2 delta over n,
Yeah, you're done.
you're done as n goes to infinity. That's the full conjecture.
That would tell you, what does the full conjecture say again? That you can.
So that means that this thing, which is the main term, which is what we expect, this is of lower order. Well, that means eventually this dominates, which means eventually this plus this is non-zero, which means eventually that number is represented.
Oh, okay, yeah. So this is a.
That's the whole conjecture.
It feels strange, like a sledgehammer for
And that we
to
should
get a positive one, right?
I would love it if we could.
No, for any
but-
alphabet, we shouldn't, right? For any alphabet, we should not be able to do that, for any alphabet, right?
Why do you say that?
Because we have n to the 2 delta over n, if delta is greater than a half, this will be greater, like this will blow up.
Yes?
And if I have that the error term is small of that, it means that actually I'll have a representation, and I should not have if that is not admissible.
The admissibility is actually being captured here in the singular series. The singular series is non-zero if and only if n is admissible. So it captures the admissibility in the process.
So that bigger is because n is admissible.
Yes. Yes, this is for admissible n. For
Okay, then I
admissible
buy it.
n.
And so really, since this is about a discrete problem, it really does not matter how close the minor arc is to major arc as long as they're different order, right? And the major arc is a bigger
Yep.
order. It really does not
Yep.
matter.
Yep.
It's really crazy. So I guess if you get a better estimate, then you might have physically, when you're simulating it, you could say, oh, it's starting here that it always works. Or
Yeah, sure. Yeah, then you would work out all these constants exactly, and then you would say, okay, here's when the asymptotic formula really kicks in, and I can guarantee that there's a representation.
but in theory, it doesn't really matter how.
If all we want is every sufficiently large, if that is the statement of the theorem, then this proves the theorem. It's like Ternary-Goldbach. You know, did Vinogradov solve Ternary-Goldbach? Because he said every sufficiently large odd number is a sum of 3 primes? Or was it until we whittled down from 10 to the, from unspecified to 10 to the 500 to 10 to the 20, and then computed the last couple? Right, so it's that kind of distinction.
I see.
Okay, so if you could get little o of this for every individual value of little n in this range, that's the whole conjecture. I'm not claiming the whole conjecture. So what I'm claiming is this on average. The claim is that it's enough for density one, it's enough to do this on average. Enough to do this.
Density one being the result of your paper.
The result of the paper, exactly. On average, which means the following: if you sum the values of n, of course, the only ones that occur are the ones that are less than n of these error terms. In fact, we can take there's a good reason to take L2 norms instead of L1 norms. This should be little o of what? Well, if each one is supposed to be n over n to the 2 delta over n, and I square that, so that's n to the 4 delta over n squared. That's each one times n. If I can get a bound that's little o of this, I claim that that will be that'll give us density 1. Let's just see that argument for a second.
This implies density.
Yes, this implies density 1. Okay, so here's the proof of the claim. Look at the set of n up to n, or of order n, doesn't matter, so that n is admissible, but not represented. So these are the exceptions. These are the numbers that there should be a bounded number of these. Numbers that are admissible, but they don't occur. Okay, I want to count how many of them there are up to n. So this is a sum over n less than n of the indicator function and of the admissible ones of the indicator function of Rn equals 0. But if Rn equals 0, then the major arcs are exactly equal to negative of the minor arcs. Right? Rn is the sum of n plus n, the main term plus the error term.
Yes.
And so if that happens, that's exactly when the major arcs, well, let's put it this way, that certainly requires that the error term be at least of the same order of magnitude as the main term.
It's smaller than equal.
Yeah. So an upper bound for the set of failures, local global failures, is this: you sum over the admissible numbers and this.
Well, this is sort of like a crude way of looking at it.
Yep. Now let me make it even cruder. We know that among the admissible numbers, the major arcs, the main term, is always of size at least of n to the 2 delta over n. So on the set of admissibles, n of order n, admissible, I have this, that the error term must be at least as large as the main term, and the main term is n to the 2 delta over n. Now you do Chebyshev. I'm going to do it, and I'm going to do it slowly. Don't worry. Okay, so I've used our lower bound on the major arcs on the main term for the admissible numbers. Now I'm going to drop that they're admissible. And now I will multiply in a quantity that's larger than 1 for every n for which this is satisfied. And what's a quantity that's larger than 1? It's, well, on the ends where this set is non-zero, where this indicator function is non-zero, the quantity, so I'll multiply in, let's do it in a different line. So I'll put in this indicator function again. The error term, what's supposed to be the error term, is at least n to the 2 delta over n. And I'll multiply in something that's bigger than 1. That'll make this only bigger. But en over n to the 2 delta minus 1 is bigger than 1, and it'll be convenient to square it. So again, the only n's which occur here are ones for which this ratio, en divided by this thing, is at least 1. And so I'm replacing the number 1 by something bigger.
Oh, okay, so this is just like, okay, so you're using this for convenience.
Yep, it's a trivial inequality.
Okay.
And then I'm going to drop this indicator function. Okay, so now that makes it even bigger, because I'm replacing 0 or 1 by 1. And so what do we have here? We have n to the 2 delta, so n to the 4 delta on the bottom, and n squared on top, and then a sum over n up to n of the second moment of the error term.
Did we lose like a -2?
The -2 is went up here.
Oh, okay, okay.
So what did we claim we could prove for the second moment? That it's little o of n to the 4 delta over n. Yep. So I have n to the 2 delta over n to the 4 delta. And the claim is that this is little o. This second moment is bounded by n to the 4 delta over n.
So this gets killed off.
So this gets killed off, and that gets killed off. So this is little o of n. And the set of numbers up to n, which are admissible but fail to be represented, is a 0 proportion. So the number of n less than n, which fail local global, fail this local global.
Talk about the moment.
Well, now forget about the moment. Look at what we were counting. We were looking at how many n's that are admissible but do not occur. We just showed is little o of n. In other words, almost every admissible number does occur. Nick, I lost you.
Okay, so we got from this upper left to the upper right.
From here?
No, next line down.
From here to here.
There to there because the 2 delta over n is smaller than.
It's a lower bound for the major arcs, for the main term contribution on the admissible numbers.
Then we expanded that.
We replaced this function 1 by the function 1 times something bigger than 1. That makes it only bigger.
Oh, sure, because when that one condition is satisfied, that's true.
Yes. Otherwise, otherwise we're multiplying by 0. So it doesn't matter. Yep.
And we got that. Okay.
And we got to the second moment. So this is called Chebyshev. Some people call it Chebyshev. I don't know.
Okay.
Some people don't even give it a name. They just call it trivial. But it's a very standard argument.
Okay.
It's a completely standard argument.
So what we were looking at originally were n less or equal to n, admissible, but doesn't get represented.
Yes. In other words, the numbers that fail the local, what should be a local global principle. They're admissible, so they should be there, but they're not. So we showed that little o of n, in other words, if you take this divided by n, that ratio goes to 0. Yeah, that ratio is little o of 1. And so the admissible numbers that are represented are 100% of the numbers.
Oh, okay. So this, what you're capturing is, right, those finite exceptions that
Yes.
should die out. And what
Yes.
you're proving is it does die out
In a density set, in a density sense.
in a density sense.
This doesn't prove that they're finite dimensions.
That's right.
This proves that, they're very sparse.
The exceptions
Okay.
are sparse. The proportion of them up to n is 0%,
Oh, okay.
asymptotically.
Asymptotically. Okay, and we did this assuming the major arcs work nicely.
Assuming both the major arcs work nicely and this, which I have to prove for. This is the main claim, that we can control the minor arcs on average. If we can control the minor arcs individually, we get the whole conjecture. If we can control them on average, we get density 1. And here's how you get density 1, out of controlling them on average.
Oh, okay, by proving this little.
This little proof tells you that this is why it's enough to control the error terms on average to get density 1.
Maybe throw away over the here function. That should be one like only very, very. It shouldn't be one very often though. We start
Right.
and then we're just making one. That's a horrible approximation, but it works.
But it works. Yeah. Yeah, that's sort of the power. I mean, if you think about what we're losing at every stage, well, we're losing a lot. The truth should be that this is big O of 1.
Right.
And we're proving little o of n. So it's indeed right at this stage, or at one of these stages, that you can say, well, where did we lose that n?
So at any point, once you guys had proven this on average, do you start like going back to this and then like trying to like squeeze, like do
To get an-
higher inequalities?
Yeah, yeah. In fact, that's so the places where we lost, we were not so careful about how close delta needs to be to 1. We just wanted some results. People hadn't even proved positive proportion.
Right.
And so that's where, as I mentioned, for Kahn and Huang, people came afterwards and tightened some of the inequalities.
But of the same method.
Yes, it's all following exactly the same procedure.
Okay, so all they're doing is doing these sort of things, but very carefully.
Not these kind of things. It's more like getting better for better values of delta, being able to prove something like this.
Mhm.
So in fact, this is the thing that we can only prove. This we can only prove if delta is near 1. If delta is near 1.
Right, so that's gonna come into play.
That's going to come into play. It's only for delta near 1 that we know how to prove this. And that's whereas for the major arcs, we can we can prove for any value of delta bigger than 1/2.
Right, that's what Leo was saying.
No, I was just saying, not the, I couldn't see the admissibility, that was my.
Yes,
objection.
The admissibility is hidden here.
And that's why it has like some sort of modular flavor, because this admissibility does as well.
Yes,
Singular series.
exactly. Okay, so let me try to give you some flavor of how you could prove a L2 bound on this.
Can you discuss a little bit of the major and the minor arcs? This is.
Yes, I will. In fact, in proving this, we will see exactly what we mean by major and minor. Okay. So let's go into this L2 norm. So we have a sum.
Yeah, we haven't defined that.
We haven't defined that exactly.
I think we have to say precisely.
Yes. So here's a little, should I make this an exercise? This is sort of obvious. So if you sum over all n and z of this L2 norm, Parseval says this is the same as the integral over the minor arcs of the L2 norm of your representation number. Andre, do you buy this? What is the error term? The error term is, again,
R is that you split them. Like this R.
Rn was split into main term and error term.
Okay.
The error term was the integral of this thing, was this Fourier coefficient, restricted to the minor arcs.
Yeah.
Okay, so if I go back to, let me just write that, it's the integral over the circle of the indicator function of the minor arcs times R n hat and E of minus n theta. So this function is E. And so the L2 norm, so now I apply Parseval. The L2 norm in the sense of integers is this.
Right.
The L2 norm in the sense of integrating on the circle, I take the absolute value squared of all of these things and integrate.
Okay, indicator gives you.
The indicator squared is still the indicator.
Right.
This squared is 1,
Right.
and this squared is exactly what's there. Okay, so
So somehow it translates very nicely.
it translates very nicely. Okay, so to integrate over the minor arcs. Now let's talk about the minor arcs. So we have a decomposition. We have this parameter m, so that all theta in the circle can be written, there exists a decomposition, there exists an expression theta is equal to a over q plus beta, where q is less than m, and beta is, so the difference, remember a over q, theta minus a over q, which is this beta, is at most 1 over qm.
Which you're getting from the.
That was Pigeonhole. So this was Pigeonhole again. So what will be convenient for us, if you remember this, r hat n of theta is a sum over gamma in a ball, gamma in a ball, e to the 2 pi I theta, and then we're picking off the 1, 1 entry. Okay, so if I put theta equals a over q plus beta, then I'm looking at this sum, gamma in a ball, and then e to the 2 pi I, a over q plus beta, times this integer, the 1, 1 entry. I haven't done anything. I'm just reminding you what the exponential sum was. And then I'm replacing theta by this expression a over q plus beta. Okay. Now here's a hint of why in the major arcs we're going to see something about the modular contribution. We can split this sum into a sum over gamma 0 in SL2Z, is SL2Z mod QZ, and a sum over gamma in this ball, where gamma is congruent to gamma 0 mod Q. I've done nothing. As a matrix, yeah. So this is the matrices in SL2Q, and now I'm restricting to what matrix it was mod Q. SL2, this is SL2Z mod QZ. Just the finite group. So what are the residue classes mod Q? And then group these by residue classes.
And you're asking for SL, you're asking for determinant 1 even in the modular case, whereas in GL you'd be asking for vertical.
That's right. That's right. That's why I want gamma A to be the even words. I forget if I said that or not.
Yeah, I think. Well, I don't think you said it today, but you certainly.
We discussed it last time.
Yeah.
I want even words in this thing.
Right. So it's like, well, you're saying that normally in the like upper half plane sense, non-modular makes little difference, right? Top or bottom, but like here it makes a big difference, was what you said.
Yes, yes. When we're looking at fractional linear actions, we could do GL2 plus, and it made no difference.
Right.
Here we really want to stick to semi-simple. Okay. So I want to write this as E sub Q of A V inner product V.
I guess I like kind of forgot why we did the pigeonhole. Like, why is it that we want the pigeonhole?
I haven't told you yet.
Oh, okay. It's not
clear.
It's not clear yet.
Okay, cool.
I'm trying to work up to it. V gamma V. Okay, so this again is just, all I've done is I've taken A over Q plus beta and split it into 2 exponentials. And the observation is this only depends on the residue class of gamma mod Q. This is an exponential sum. This is the usual e to the 2 pi over Q. This is an integer. A is co-prime to Q. Doesn't matter, whatever this is to an integer. It only depends on the residue class of gamma mod Q, not on the exact value of gamma itself. So I can put a 0 there. And this gets pulled outside. Okay.
Wait, can you explain why we can replace gamma for gamma 0 then?
Yeah, because this is an integer. This is in Z.
No, this is yes.
And this only depends, this is a character on Z, additive character on Z, that only depends on the residue class of this mod Q, on this whole integer mod Q.
Okay.
Well, that means all that matters is what gamma is mod Q. What the reduction of gamma is mod Q. but we've grouped it by the residue class precisely so that we can pull this factor. We're separating the modular and Archimedean components.
Before it was, you have the literal gamma.
Yeah.
Then you're just saying mod. Okay.
Right.
So this is the modular and Archimedean is the.
Is this part? Yeah, sort of this part will be Archimedean. This part will be Archimedean.
It's all you're doing here, you're separating it into equivalence classes, essentially.
Yep. And this will turn into the singular series. This part is what will turn, this is the modular component.
Will turn literally like the definition of the singular series in this case, or
It-
after further work?
After further work, because you have to put it back into the major arcs integral.
Okay, oh,
Okay. All I want to get out of this expression is that if we're going to have some hope of not having cancellation, if we're in the major arcs, then this is a number that's generically of size n. And so this beta had better be of size very close to 1 over n. I don't want, if we're in the major arcs, I want here not to have cancellation. I want to capture the modular conditions, that even odd condition, but I don't want cancellation in the Archimedean part. So I want this beta to be no bigger than 1 over n in the major arcs.
It's MN, right? Major arcs N.
Yes, so I haven't said, I'm building up to the value of m that I will choose for the Dirichlet, the level of Dirichlet approximation.
I'm just saying we make the findings from the major arcs as N changes.
So I haven't defined the major arcs.
Yeah. Okay.
I'm working up to the definition. And you see this, if Q is as large as m, this can get as large, this can get as small as 1 over m squared.
Yeah.
And so if we want in the major arcs, this beta to be of size 1 over n to match this n, then we will choose, so we choose m to be root n. Okay, so the first choice that we've made is just what is the depth of Dirichlet approximation. And that's purely based on this kind of analysis.
so what you did was you're saying how many bins do we want before we can that's what this M was controlling.
Yes, well, that was the proof. The proof was about controlling the bins. But now I want to know what's the tightness. I'm trying to define these major arcs.
Right.
So how tightly nearby them do I want to allow things? And I want to allow things ever so slightly larger than 1 over n in beta, it to be in the major arcs, because n is the size of the thing that's being multiplied by this. And so this exponential sum had really better not fluctuate too much.
I'm just like, what would be a bad way to tweak this is what I'm wondering. What happens if you let one beta be huge?
I just won't be able to control things. I won't be able to get estimates.
Because it'd be hard to
Effective
predict what
estimates.
happens.
Sorry?
It would be hard to predict what happens.
It'll be hard to get control on, so what's needed, what will be needed in the major arcs is control on sums with some fluctuating parameters. What will control the fluctuation is the derivative of this function. And if the derivative is too large, then I can't control the sum.
And so it won't hurt if beta is smaller than 1 over 1?
Smaller is better. Smaller is that I'm even closer to a fraction with small denominator. Okay. And I need to be able to do this uniformly in progressions. So that's all. Maybe I'll try to say something about that, but that's coming later. All I want to do is motivate the following decomposition. So when we're summing these e thetas squared over n, and we've expressed it as an integral over the minor arcs of rn hat theta squared d theta, what I want to do is break this major arcs into dyadic components. So the minor arcs. The minor arcs is the set of all theta equal to A over Q plus beta.
This makes sense, right? Because the minor arcs are almost everything.
They're almost everything.
So the dyadic thing will tell us. something.
Yeah, I want to break it into dyadic values of Q and dyadic values of beta. Okay. So let me write it like this. These major arcs are covered by unions of things called W, let's call them WQK, where I want to collect WQK for parameters Q and K. WQK will be the set of all theta equal to A over Q plus beta, where Q is of order Q. In other words, between Q and Q over 2. A is co-prime to Q. So A ranges from 1 to Q. Right, we're in the circle. And beta is of order K over N. K over N because we chose M to be root N, and the largest, this range will be like 1 over N. So I want to have a parameter K that controls this range. You'll see in a second where this is, where I'll show you a picture.
Can you repeat the last part? Choose K over N, say 1 over 2K over N, until K over N.
Yes.
Because M.
I'll show you right now. Here's how I think about these regions. Okay, so I claim that this is bounded by a sum over Q less than M. M is root N, N to the half. This is a dyadic sum. In other words, you go from N to the half to a half N to the half, from M to M over 2, from M over 2 to M over 4, M over 4 to M over 8, and so on. And there's only log of these. So the number of these is bounded by log N. So I'm losing logs by doing things dyadically. And then I sum over K. Now, what's the range of K? How big can K get? Remember that A over Q, theta minus A over Q, in other words, this is beta, is bounded by 1 over QM. That's the Dirichlet approximation. And I'm saying this is of order K over N in this set WK. And M was chosen to be root N, and Q is of order big Q. So K is at, yes, exactly. So K is bounded by square root of N over Q. So I'll take K less than root N, also root N, the same root N that occurs here because of the choice of M over Q, again dyadic. So I have this dyadic decomposition of the integral over WQK of Rn hat squared. Let me show you how I think about these things.
And at this point, this is all like specific to the problem.
Now we're starting to set the parameters based on the conditions of the problem.
At this point, for some other context, you might not be able to,
That's
it
right.
might not be like, oh, it's best to do this dyadic or like.
That's right.
Split intervals like this.
That's right. Okay, so let me show you how I think about these things.
What's the symbol that looks like a top and a count?
This thing?
Yeah.
Sorry, that's I should have said that earlier.
Up and down.
This is that there are constants above and below. So G is less than F, and F is less than G, then F is of order G.
Yeah.
Okay.
So be bounded between two constants. In number theory, people often write a squiggle. This really bothers me. Squiggle means asymptotic.
Oh.
In every other formula, in that same number theory paper, squiggle means asymptotic, except when it's a summation, and then squiggle means dyadic.
Oh, that's terrible.
Everyone knows this. Everyone, does it, and it's been the
By
tradition
context,
for.
you would read it, I guess.
Yeah. In context, you just get used to, depending on whether it's under a summation or
Oh,
right next.
yeah.
Like there's like a sum of n squiggle n is squiggle something, and where this squiggle means asymptotic, and that squiggle means dyadic range. So I'm trying to break with that tradition by systematically using this notation.
That's great.
Over W?
Yes, so I'm taking the integral over the minor arcs will be, now I haven't said anything, so
Over dyadic regions,
yes.
integrate over that diagonal.
So once you've decomposed things into dyadic regions, then I can really show you how I think about major and minor arcs.
And dyadic regions are Q and K.
Yes,
Please go again.
yes, I'm sorry.
Oh, Lewis.
You never noticed that, right? Yeah, the two uses of squiggle. Look at any paper, look at any number theory paper, you will see those two uses of squiggle in the same formula. And you're supposed to know, and of course it's easy enough to
This
learn.
part of the Landau notation, is this used by computer scientists as well? The top cut, bottom cut? Or-
No, not that I know of. I don't think I think this is still sort of standard number theory,
Interesting.
but not elsewhere. Okay, so if we're going to think about this dyadically, then what we really want to do is capture the power of n. So q, well, I'll write as n to the alpha. So alpha ranges up to a half. Okay, and k, well, and k I'll write as n to the kappa. Hopefully you can distinguish my kappas and k's, even though it's not printed, where k times q is less than a half. In other words, kappa plus alpha is less than a half. So this is coming from the fact that k times q is less than n to the half. Okay, so I have the following picture in my mind of the circle. The circle 0, 1, I think of as here's kappa and here's alpha. Alpha goes up to a half, kappa goes up to a half, and alpha plus kappa is at most a half. That's this line. So this is the circle. That's the circle.
Because those parameters are going to control.
That's going to control the size of the denominator, and it's going to control the distance from that fraction.
So that's what K is doing.
Yes.
Q.
If k is very small, if k is less than kappa 0, and q is very small, if q is less than n to the alpha 0, what is this little square?
So you said again, alpha is controlling how big Q is. And
Yes.
Q is controlling.
And and kappa is controlling how big beta is.
That's the major.
That's the major arcs. That's the major arcs. Right here is the major arcs.
Because you have, means you're close.
You're
to-
very close. You're very close to a rational with very small denominator.
That's
Okay,
That's major.
that's the major arcs. Okay, everything else is minor arcs, and we need to get cancellation on everything else
When partitioned like this.
when partitioned like this. So I have to add one more thing to this sum, which is I only want to consider this when how shall I write this? When either Q or K are larger than Q0, so Q0 will be n to the alpha 0. That's the parameter that determines that when your denominator is small enough. And kappa 0, K0 is n to the kappa 0, which determines when you're close enough to that fraction. So you're only in the minor arcs if either or both, if at least one of Q is at least Q0 or kappa is at least kappa 0. So that's all part of the conditions of this summation. If Q is less than Q0 and kappa is less than kappa 0, you're not in the minor arcs. You're in the major arcs, and you shouldn't be estimating the minor arc contribution. Okay,
And then,
so this is all minor arcs.
so what is going to be small for alpha and kappa?
They're going to be tiny powers of in other words, Q0 is a tiny power of n.
Q0
One
T.
over 100, like the distributed.
So
It's 1 over delta minus 1 times theta, where theta is the spectral gap. It's a parameter that takes a lot of work to specify exactly. And it comes from it comes from this count. What I said about you need to be able to count efficiently in progressions uniformly as Q ranges in terms of n, there's a parameter there from the spectral gap. And that parameter is what goes into alpha 0 and kappa 0. So there's some way of determining those major arcs. Never mind what that is for right now. The first thing I want to do is get a bound on the minor arcs.
So did you actually do the analysis this way? Did you first, like, you're like, I'm not sure what alpha 0 and kappa 0 are going to be,
Exactly.
but I'm going to split it diagonally like this and see if
Yes,
it works. And if it does, I'm going to push really hard to,
exactly.
oh, okay.
To know this a priori, it must be very difficult.
Right. So it wasn't that you knew that you had good control over alpha 0 and kappa 0 and then went to work on the rest of it.
So far, I think of everything that I've said to you as being completely standard analytic number theory. I haven't done one, modulo the fact that we're in this setting. I mean, as far as the circle method is concerned, modulo the fact that we're in this group setting. So this orbital circle method and orbital sieve methods, that's new. Applying it to the setting of thin groups and applying it to the setting of groups at all is new. But the way in which you analyze it is completely standard so far. What we've done so far. And now I'm out of time. What we will do next time is we will start with this and we will estimate this in L2. We'll estimate this dyadic interval, and we'll see that as long as kappa or Q are sufficiently large, we can get cancellation. Okay, so we'll be able to get cancellation in all of the minor arcs.
You said sufficiently large.
As long as there's some, so there's going to be some region. Again, you have to marry the major arcs with the minor arcs. So the minor arcs will have cancellation as long as kappa is at least something. The major arcs will be able to get a main term as long as kappa 0 is at most something.
If you don't get intersection, then you're in trouble.
If you don't get intersection, you don't have a theorem.
That's fair, that's fair.
Okay, so there's going to be some range of kappa, and if you're far away, we should get cancellation. If you're far away from that fraction, A over Q. If the denominator is large, even if you're close, we should get cancellation. There'll be different reasons for why this happens. We'll capture those, and then once we capture all of those, we'll have the minor arcs as long as we get major arcs large enough to completely cover the circle. So this is my view of the circle. And it's in terms of this dyadic decomposition of the parameters.